toxic waste, child labor, and a finite resource countdown. These are the foundations of your electric car's battery, the heart of the green revolution. We're going far beyond the charge port today, diving into the whole ugly life cycle of the EV battery. What materials go into it, the environmental damage caused by getting them out, and the massive logistical mess of trying to reuse them. We'll show you exactly why your clean commute is subsidized by some of the dirtiest supply chains on Earth, and why it's important to extend their lifespan for as long as possible. If you think recycling is a simple solution, stick around, because we're revealing the inconvenient truth about what happens after your EV car battery hits the wall, and why the industry is fighting a battle it's currently losing. We're about to drop some knowledge that might just change how you see your next vehicle purchase. Lithium-ion batteries are often made up of thousands of individual cells, all working in concert. It is a highly sophisticated orchestra of tiny powerhouses packed with exotic ingredients: lithium, cobalt, nickel, and manganese, among others. Each of these elements plays a critical role in how efficiently your battery stores and releases energy. The whole assembly is managed by an incredibly complex battery management system. How long do these miracles of modern chemistry last, you ask? Well, unlike your grandma's old flip phone battery that barely held a charge after a year, EV batteries are built to last. Most manufacturers offer robust warranties, typically around 8 years or between 100,000 to 160,000 miles. During this first life, the goal is for the battery to retain at least 70% to 80% of its original capacity. Below that, the reduction in driving range becomes significant enough that it's just not practical for most vehicle owners anymore. It's like trying to run a marathon with one shoe. You can, but it's not ideal. But here's the rub, and it's a big one. Getting those magical materials out of the ground is where things get a bit dirty. Let's be brutally honest. The mining of these raw earth minerals for EV batteries is not a clean process. We can't just pretend it's all rainbows and zero emissions from day one. In fact, the initial manufacturing of an EV battery is currently the most carbon-intensive part of an electric car's life cycle. The majority of lithium supply comes from brine operations in places like the Lithium Triangle in South America. The extraction process consumes millions of liters of water per ton of lithium. In already arid regions, this can severely deplete local aquifers, impacting indigenous communities and vital agriculture. Plus, the chemicals used and the leftover brines can easily contaminate precious freshwater sources and soil. Next, cobalt. Oh boy. Most of the world's supply comes from the Democratic Republic of Congo, and this is where the environmental issues intertwine deeply with devastating social and ethical ones. Cobalt mining is notorious for severe acid pollution, heavy metal contamination leaching into waterways, and air pollution from dust. But even worse, it's often linked to child labor, horrific working conditions, and forced displacement. And finally, nickel. While maybe not as headline-grabbing as cobalt, nickel mining has its own set of problems. Its processing is incredibly energy-intensive, often relying on dirty energy sources, meaning higher greenhouse gas emissions. Plus, the waste from nickel mining can lead to serious heavy metal contamination in local ecosystems. So, yeah, it's a harsh reality check. We need these materials to save the Earth, but the current methods of acquiring them come with a steep price. This is precisely why reducing the need for new mining as much as humanly possible is so incredibly vital. Just because your EV's range has dipped to 70 to 80% of its original capacity doesn't mean the battery is useless. Far from it. It's simply not performing optimally for a vehicle anymore. Think of it like an aging athlete. Still incredibly strong, just not quite as fast as they used to be on the track. This is where second life applications come into play. Used batteries can be extracted and repurposed for less demanding applications, which extends their useful life for at least another 5 to 10 years. Stationary energy storage is the main application. When installed in residential and commercial buildings, they store excess solar energy and power the buildings. Some become part of massive grid-scale storage systems, helping to stabilize power grids and integrate more renewable energy. companies are literally building giant battery farms from retired EV packs to back up entire neighborhoods or facilities. Used EV batteries can also be used in non-road vehicles, such as electric golf carts and warehouse forklifts, where the power demands are much lower. It's an incredibly smart way to squeeze every last electron out of these expensive and resource-intensive power packs before considering recycling. Eventually, even second life batteries reach their end when their capacity finally dwindles too low, or if they're severely damaged. That's when recycling takes center stage. This isn't just about saving the planet. It's about pure economics and resource security. Modern recycling facilities are becoming incredibly sophisticated. They're designed to safely dismantle battery packs and then use advanced techniques like hydrometallurgy or pyrometallurgy to recover valuable materials. Such techniques can get back almost all the nickel, cobalt and copper, and increasingly lithium too. The recovered material can be used to make new batteries, creating a truly circular economy. This reduces our reliance on new, virgin mining, cuts down on waste, and ultimately makes the entire EV ecosystem far more sustainable. It's the ultimate closed-loop system, getting us closer to a truly green electric future. Sounds like a dream, huh? Well, no. Hold your horses. The idea of recycling old batteries is a nice thought, but the reality is a logistical nightmare, posing a huge supply chain challenge for scaling up the second life market. Sadly, it's been estimated that only 5% of lithium-ion batteries are recycled globally, with the rest ending up in stockpiles for recycling or reuse at a later date or in landfills, which could lead to disaster. A study from Australia found that 98.3% of lithium-ion batteries end up in landfills. In the UK, lithium batteries are responsible for 48% of all fires in waste processing facilities. So, what gives? First is the great data gap. Automakers own the battery's service history, and getting that detailed performance data, the exact state of health and previous usage cycles, to a third-party repurposing company is like pulling teeth without it. Repurposers have to spend a ton of time and money just testing and grading each massive pack. Imagine buying a used engine and having to run it on a dyno for a week just to find out how much power it's actually making. That time and cost cuts directly into the economic viability of a second life project. Next, there's the terrifying reality of hazardous transportation or dangerous goods. If you thought bringing portable power banks onto aeroplanes was a nightmare, try shipping EV batteries, new or used. You can't simply slap a 1,000-pound lithium-ion brick on the back of a flatbed truck and ship it across the country. These batteries are classified as hazardous material, especially once damaged or retired because of the risk of thermal runaway. They have to be discharged to a safe state of charge, packaged in specialized, explosion-proof containers, and transported by companies with specialized certification. All of that adds significant complexity and cost, sometimes making the transportation alone 40% of the entire recycling or repurposing bill. It's often cheaper, in the short term, to just pay for new raw materials than to deal with the headache of moving the old, unstandardized packs. Third, there are limited EV battery recycling facilities worldwide. Europe only has 2. The supply exceeds the recycling capacity. The final punch: lack of standardization. Every car maker builds its battery pack differently. Different sizes, different chemistries, connectors, and management systems. Repurposers can't just use a single, efficient assembly line. They have to develop bespoke processes for nearly every model that rolls through their door. This friction in the reverse supply chain is the biggest obstacle to getting a steady, cheap flow of retired power packs to the people who want to turn them into battery farms. So, there you have it. The EV battery journey is a complex yet promising one. From the dust of the mines to powering your daily commute, and then hopefully to a second life, and finally back to being reborn as new materials. While it's not perfect yet, and there are many hoops to jump through, it's also not all doom and gloom. The trajectory is clear: less mining, more recycling, and a genuinely sustainable energy future. To accelerate this, we need to drastically change how we source and manage all resources. If not, we're not solving the problem. We're just moving it somewhere else. So, what's going to happen with your current EV battery? We're watching,